Well, you see, it has 4 different protein structures. It has primary, secondary, tertiary, and quaternary.
You tell me, girl.
I'm telling you, the primary structures are linear sequences of amino acids. These amino acids are joined together by peptide bonds.
You know that I just say it's the same thing I just say. Continue.
But I'm just showing you that I know my work now. Now there are 2 types of secondary protein structures. It has the alpha helix and the beta pleated sheets.
So before you further, you could make this chart look a little bit better. You are not listening in your room. Continue.
Who's studying from them?
Continue.
And then it has the tertiary structure. These are spatial arrangements of amino acids. So you remember that?
Yeah, I'll try to.
Then it has the quaternary. These are spatial arrangements of polypeptide subunits. But okay? You can see how you need to buy my glasses. Alright. Interactions between the side chains of amino acids determine how likely the chain will fold. I can see that.
So here what I say, it's something like this, right? Now when the polypeptide chain being synthesized and it coming out of the ribosome, nice. As soon as it coming out of the structure here, they then begin to form. Right? So because it start folding, as soon as it coming out of the ribosome, part of it might attain its tertiary structure while the other part inside the take form as yet, right? Nice. So, as the amino acids start to fold, right? Some of them may attract and some of them may repel each other, right? Now this is due because, oh Lord, like I can't spell attract and repel.
I know you can't spell, you just like to play it.
I use my friend.
I can write and you can't spell.
Some of them may attract and some of them may repel. Why do you think that is so? Attract and repel. Simple physics. No. Simple physics is a chemical kind of thing going on there, right? The
chemical.
What is that? Chemical properties, right?
Okay.
No. This interaction thing, it has other kind of interactions that is alter the folding and how they bond with each other. No.
Okay.
It have the hydrogen bonding, the disulfide bonding, and the wells.
I don't know, you tell me?
Let me look here. It is hydrogen bonding, the hydrophobic interaction. Chaperone. Chaperone.
Like a chaperone?
No. Chaperone, right? This structure here does assist with detecting misfolded proteins, right?
Johnny, wait now. That is not your old girl Palmati and she's pregnant?
Yes.
Oh my God. What you do? Doc, what we have going on here now?
Well, we got some DNA samples from the blood, and well, as you can see, he has samples to the chest, and look at his wrist. It looks like there was a struggle. But we'll know more when we get results back from the lab.
Ma'am,
What are they doing in the house?
what went on here, ma'am?
Yeah, the knife.
Ma'am, we'll have to take it down to questioning, okay? So you can leave with us.
Good morning.
Good morning.
How are you feeling today, ma'am? You've been unconscious for a while.
What's wrong with my leg?
Well, yeah.
Oh, my baby!
I'll go get the doctor.
Go quickly. Ma'am?
Honey, let me see. Let me come. Let me take a
Preeclampsia is basically a condition that occurs in the second half of the pregnancy, and it is characterized by the formation of supramolecular aggregated misfolded protein that is present in the urine of the mother as a result of damages done to the kidney, which is the filter system. Well, in order to understand why it is a protein misfolding disease, we must understand what is protein misfolding. In order to carry out the essential functions that protein would normally carry, they need to basically to conform into intended shapes or intended conformation, and these are basically three-dimensional structures. For instance, let me say this is a protein molecule, right? We see it as the protein molecules. Now, in formation of this protein molecule, we have polypeptide chains, and these polypeptide chains are formed by sequences of amino acids, and the sequences of amino acids are specific, and they are held by intermolecular forces, they are held by hydrogen bonds, and these intermolecular forces, hydrogen bonds, etc. are responsible for holding these molecules together, which then form this protein molecule. Specific formation of a three-dimensional conformation, which will then allow the protein to function. Now, if we don't have this three-dimensional structure being formed, then we have a problem, right? We have unactive or environmental factors. Remember, we're dealing with the body and the whole. And in the body, we have pH, we have temperature, etc. And these factors could influence the formation of a 3D protein molecule. For instance, pH. Now, if the body doesn't have a particular pH at which this three-dimensional protein could form, what could happen is that pH could affect ionic bonds. It could affect van der Waals forces present in it, intermolecular bonds that is in this three-dimensional structure. Remember, temperature plays a vital role in regulation in the body. Also, it can affect the formation of this three-dimensional structure in that if you have a too high temperature, it can affect bond formation. It can cause breakage of bond. Or if you have a too low temperature, it can also affect the formation of this three-dimensional structure. Now, one of the things that we utilize to identify misfolded proteins through science and technology now, we can identify is that we utilize a dye. This dye basically has an affinity to misfolded proteins, so it is specific to conformation. So what it does is that once it identifies a misfolded aggregate in the urine sample, it will immediately bind to it and give it a color change. Okay. Right? So we need to understand our dye. Now the next thing we need to know is that, as I mentioned to you before, is that we protein clump together. So we deal with clumps. Now the first thing we need to know is that this is our sample here before we stained it with the dye. So you realize that in preeclampsia, we utilize the plasticine, the blue plasticine to represent the protein that has not been stained as yet, right? So we have the clumps of the protein. Now what I did is that I took the same sample of the patient that has the preeclampsia with the clumps of protein, and we stained it with red dye. Now if you notice that in the sample containing the protein aggregates, is that the dye basically bind to the clumps of the protein and gave it a red color. The red color basically shows that these proteins are misfolded proteins, because only if the proteins are misfolded would it bind. Now, and we also took a sample of a patient that is normal in pregnancy, that doesn't have high blood pressure, and we just want to show you that in the urine collection, if you realize it's just a very little amount of protein that is present as compared to the person that has. I wanted to show you a small demonstration of how the kidney works in both cases of a normal patient, as we see here, a normal patient that has relatively normal blood pressure. Here, so we're utilizing the filter paper, which would represent the membrane of the kidney. So we see that the membrane of this kidney here, the spaces between the membrane and the cells are relatively small, they are narrow, so that it will allow only small substances to go down. And we also have a setup here where we have a patient that has the preeclampsia. We have the patient that has the preeclampsia, and we allow it to run through this basically setup. It shows the kidney under high blood pressure. So we have large pores formed in the filter system as a result of the high blood pressure damages to the wall. Now, if you realize that because of the large pores, the proteins were able to get into the urine as a result of this large normal person that has normal blood pressure and the urine consists of a little bit of protein present, what happens is that because of the narrow walls, only the useful substance such as water would be able to pass through and not the protein because of its relatively large size. What happened?
Mom, this is no joking matter. What really happened?
Ma'am, we need to know what went on. Why were you holding the knife? Why was your daughter on the ground? What happened?
She pretended that she's serious.
Ma'am, what went on? Come on, we need to know.
What are you talking about?
You think pretending you don't understand will help you get out of this grave?
What are you talking about?
The results came in for the CT scan.
Oh, let's have a look. Well, based on the results, it looks like the person is positive for Alzheimer's.
Based on these results.
Yes, because as you can see, the cortex shrivels up and damaging areas that is involved in thinking, remembering, and planning.
I'm not seeing anything there.
Well, Alzheimer's is a protein misfolded disease, so let's have a look at that, and probably that will clear up things.
I feel so.
Okay. Protein misfolding can either occur spontaneously or can occur as a result of mutations in genes. In Alzheimer's, it can either occur in either one of these four genes, either APP, PSEN1, PSEN2, or APOE. In APPP, this is the amyloid precursor protein. Mutation changes the protein building block in the amyloid precursor protein. And this mutation replaces the amino acid valine to the amino acid isoleucine at position 770. This results in the increased amount of amyloid beta, and this increased amount of amyloid beta that accumulates in the brain, and as a result, it results in the clumping, which is characteristic of the disease. Whereas in the PSE1 gene mutation, this mutation changes the building blocks of the DNA. When it changes the building blocks of DNA, it disrupts the normal role of the presenilin 1. And since this is disrupted, it disrupts the normal processing of the APP. And this results in a mutation that causes amyloid beta to accumulate. And when this amyloid beta accumulates, it forms amyloid plaques that is characteristic of the Alzheimer's disease. Now the PSEN2, it has two common mutations that result of PSEN2. One of the mutations is that the amino acid asparagine is replaced with the amino acid isoleucine at position 141, and another mutation can occur in which methionine is replaced by valine at position 239. These mutations, that is the replacement of the amino acids, tend to disrupt the normal processing of the APP, and as a result, amyloid beta accumulates in the brain. And when amyloid beta accumulates in the brain, it can result in the formation of amyloid plaques. And once these plaques are formed, they are characteristic of the Alzheimer's disease, and when they accumulate, they can become neurotoxic, and as a result, causes the interrupts in normal function of the neurons and can cause signs and symptoms that are associated with the disease. How these abnormal structures, amyloid beta and neurofibrillary tangles, are two biologic factors of the Alzheimer's disease. Let's talk about what happens in the formation of the amyloid beta. When in Alzheimer's, the enzyme called beta secretase makes the first cut at the APP. Makes the first cut at the APP, so the beta secretase first cut So the gamma secretase comes and cuts it, and the APP, short fragments of the APP are released. These short fragments of APP are called amyloid beta. When the amyloid beta accumulates, it becomes toxic and it disrupts the normal function of the neurons. And as more fragments are added, these oligomers increase in size and become insoluble, and as a result, amyloid plaques are formed. Now, as I mentioned just now, I said that only are two biologic factors. One was the amyloid beta, and the other one is the tau, is the neurofibril fibers. Protein called tau, in its healthy version, is used or helps in the assembly of the microtubular structures, and these microtubular structures act as tracks guiding nutrients from the body of the cell to the axon and then back. In Alzheimer's, the tau undergoes chemical changes and becomes hypophosphorylated. It then begins to pair up with other threads to form neurofibril fibers that disintegrates the neuron transport system.
Who run the world? Yes! Who run the world? Yes!
Major laser.